Hi, I'm Alistair, and this is an electronic escape room puzzle that's all about providing the right conditions to make some flowers grow. So here I've got some plant pots, and I've also got a controller with 3 sliders on it. These sliders control the light source above the plants there. So moving the left slider up makes the light turn red. If I move the middle slider up, that makes it turn green. And the right hand slider makes it turn blue. And by blending those 3 primary colours together, we can make that light turn any colour we want. So if you remember colour theory from school, you'll know that if I keep the red slider off and move the blue and green sliders up, we'll make cyan light. Now if I turn the blue slider down, keep the green slider up, and instead move the red slider up, we'll get red and green, which makes yellow light. And this makes the flower in the middle, which has got matching yellow petals, grow up towards the light. Now if I change the light to something else, the flower will stop growing again. So flowers will only grow when the light is set to the correct colour that matches the colour of their petals. If I move it back to yellow again, it will carry on growing until it fully blooms. Now, if I pull the green slider down and instead push up the red and the blue sliders, we'll get pink light. And now the flower on the right hand side, which has got pink petals, will grow. Now, these are analog sliders, so you don't need to move them all the way up. You can adjust them gradually. And the last flower on the left-hand side here, this has got purple petals. So to make purple, I'm going to need red and blue, just as I did with the pink, but much lower intensity, much darker. So I'm just going to pull red and blue up a little bit until I get purple light. That's going to make the final flower grow. And now, once all the flowers have bloomed, I'll just wait for that one to get to the top, you could have a message or an item or a code that's written on the stems that's only visible when they've fully grown, or you could trigger any other action you wanted once they're all fully extended. And in the rest of this video, I'm going to show you how I made this puzzle and how you can create it yourself. So let's start off by looking at the hardware I'm using. The flowers are mounted on the end of 8-inch linear actuators. The flowers themselves, I bought these off eBay. These are fake Cuban bulrushes apparently. And I just 3D printed a little mount like this, which allows me to arrange them and place them on top of the shaft. This is a regular plant pot, which I've just cut a hole in the base, so I can feed that through the actuator and put the flowers on top like that. Now, I've used linear actuators in a couple of projects before, but if you're not familiar with them, they're somewhat like DC motors, except that instead of spinning round and round in a rotary motion, they move up and down linearly. They have 2 terminals, and if you connect those terminals to a DC power supply in one direction, they'll extend. If you reverse the polarity of the supply, so swap the positive and negative terminals over, they will contract instead. Now, they're not very fast and they can be quite noisy, but they're really easy to use. They have built-in limit switches. That means they will automatically shut off when they reach fully extended or fully contracted position. And they don't need any sort of control signal like you would with a servo or a stepper motor. You just supply power to them and they do their thing. So to control these actuators, I've got them wired to this relay module at the back. And in order to be able to reverse the polarity and change their direction, each actuator actually uses 2 channels on that relay. So this is an 8-channel relay module. And to be able to control the 3 actuators, I'm using 6 of those channels. The other 2 are spare. Now the inputs I'm using, these are sliding potentiometers, and these are being read using 3 analog input pins on an Arduino UNO. That's then interpreting the positions of the sliders into an RGB value, which is what's being used to set the colour of the light. Now, I've used programmable LED light strips in lots of projects like a WS2812B, which have a data line directly connected to the GPIO pin of a microprocessor. But for this project, I wanted to use a more prominent light source. So I'm using this stage wash light. And like most theatrical stage light units, this is controlled by a DMX interface. So DMX is the industry standard used in stage effects, has been for years. It's robust, it's simple to use, and it's very widely supported. And the way it works is that you can daisy chain lots of DMX devices together in series to create what's called a DMX universe. Now, each of those devices could be a light like this one, it could be a spotlight, a strobe, a laser, a fog machine, and each fixture is assigned one or more channels in the DMX universe that control different aspects of its behaviour. Now, you're not limited by the number of fixtures, but rather by the number of channels. So a universe can have up to 512 channels of data, but you might have several fixtures that are all controlled by the value of the same channel. So for example, I could have lots of identical lights to this one, all connected in series, and they could be synchronized together by all listening to the same channel. Now, the DMX controller, which is an Arduino UNO in this case, sends a packet of data that contains a byte, 1 byte value between 0 and 255 for every channel in the universe. And that packet gets passed along to all the devices, with each one only acting upon the value of the particular channels that it's assigned to. Now, I'm only using a single light, but this actually uses 3 DMX channels because the red, green and blue values are sent in separate channels. In fact, a single DMX light might have many more channels than that, because they can also be used to control things like movement, rotation, or control other special effects. Now, the physical interface I'm using to take that DMX signal from the Arduino UNO to the light is using a DMX shield that's mounted on top of the Arduino. And even though Arduino UNOs are pretty old now, and I more often use ESP-based boards for most new developments, they're still incredibly useful because there's still so many ready-made shields available for them that add all sorts of additional functionality. This is not a particularly demanding project in terms of code complexity or processing or memory requirements, so a humble UNO is just fine. And the DMX shield provides an input and output port to connect a 3-pin DMX cable, which is then wired to the light. Now, you could use a more modern processor instead, like an ESP32 or Raspberry Pi, and then add your own DMX interface to it. That's actually not that hard to do, since DMX is based on the RS485 serial interface standard. And you'll find plenty of example circuits that will show you how to build one of those using a transceiver chip like a Maxim Max 485. Now, if I remove the back panel, you can get a clearer look at those components. So I've got my 8-channel relay and my Arduino. They're both mounted onto a DIN rail on the board here. The black cables here, these are coming in from my linear actuators. So I've got my first actuator going to the common terminals of the first and second relay channels. My second actuator is going to channels 3 and 4. My third actuator is going to the common pins of channels 5 and 6. I've then got the normally closed terminals and the normally open terminals of all of the relay modules daisy chained together, and those are going to the positive and negative terminals of this 12-volt DC power supply, and that's what's going to supply power to the actuators. Now, the relays themselves are controlled by this bundle of signal lines here, and those are wired to the GPIO pins on the Arduino. The Arduino has got the DMX shield stacked on top of it, and we've got the DMX out port here. That's what's wired to this 3-pin XLR connector, and that is going to our light fitting. And then we've also got this bundle of yellow cables at the back. Those are going to the analog pins A3, A4 and A5, and those are connected through to our sliders here. And here's a diagram of that wiring. So we've got our Arduino in the middle with a DMX shield stacked on top of it. And the only connection we're making to the DMX shield itself is from the DMX out port here, and that goes to the DMX in of our light fixture. Now, if you wanted to control more lights from the same Arduino, you could extend the DMX universe by wiring from the DMX out of this light fitting to the DMX in of the next, and so on, daisy chaining them together in series. But we've just got a single fixture, so we've got a nice simple connection there. And then we've got our other components wired to the regular GPIO pins of the Arduino. We've got our 3 linear potentiometer sliders, and these are wired to 5 volt, to ground, and to one of the analog input pins, A3 to A5. And the way that these sliders work is that they act as a voltage divider whose output ranges between the 2 input voltages according to how far up the slider has been pushed. So when it's all the way at the bottom, the output signal that we read on this yellow wire here will be 0 volts, same as ground. And when it's pushed all the way to the other end, it will read 5 volts. So we can determine the position of each 3 sliders by taking an analog read on the Arduino pin that the output is connected to. Now, one of the problems with analog signals is that they can be a bit jittery. And if when you come to build this, you find that you have problems getting a nice clean reading from the analog output of these potentiometers, you can try adding a capacitor across the 5 volt and ground lines close to them, as I have done here. And that's going to smooth out the power supply, which should give you a cleaner signal. But you might find that you don't need this. It will depend completely on which components you're using. So you can leave it off to start with and only add it in if you feel necessary. And then on the other side of the Arduino, we've got the control signals that are going to be used to turn the relays on and off. They're wired to GPIO pins 6 through to 11. And we've also got a 5 volt DC power supply here, and that is powering both the Arduino and also the relay module. The DMX light, incidentally, is powered from its own mains power supply. The DMX cable is only ever used to carry control signals. It doesn't take power to the device itself. So then on the load side of the relay module, we've got our linear actuators. Now they've each got 2 wires, and those are connected to the common terminals of each of the relay channels. And they're connected in pairs, so the first actuator is connected to the common terminals of channel 1 and channel 2. The second actuator is connected to channels 3 and 4, and the third actuator is connected to channels 5 and 6. And then the normally closed terminals of each of the channels are connected all together in series, and they are connected through to ground. And then the normally open terminals of all the channels, they're also connected together, and they are connected through to the positive terminal of this 12 volt power supply here. This is what's going to be used to power the actuators. Now, what this means is that by writing a high or low signal to any of the GPIO pins 6 to 11 here, the Arduino causes the corresponding common terminal on the load side of the relay to switch between either ground or 12 volt. And the actuators are wired in pairs to these 2 relay channels, so we can consider them acting as pairs together. So if we switch channel 1 to the normally closed side, that's ground, and if we switch channel 2 to the normally open side, which is 12 volt, the first linear actuator will have 12 volts connected across it, and it's going to extend. Now, if we switch channel 1 to be the normally open terminal, which is 12 volt, and we switch channel 2 to the normally closed terminal instead, we'll have reversed the polarity of that 12 volt. Our current will flow in the other direction, and the first actuator will contract instead. So if the pair of relay channels are set opposite to each other, we're applying a voltage in one direction or another and the actuator is going to move. If both relay channels are set the same, either both open or both closed, there's going to be no voltage difference across the actuator contacts. They'll either both be at ground or they'll both be at 12 volts. In either case, no current is going to flow, so the actuator will stay still. So using two relay channels like that is a very useful pattern for controlling anything like a DC motor, a fan, an actuator, anything where you want to be able to reverse the polarity of a current across a device. It's a very useful technique. So here's the code that's running on the Arduino. Starting at the top, so we're including this single external library which you can download from this GitHub link here. This is the DMX Simple library written by a chap called Paul Stoffregen. Now, Paul is a prolific developer of Arduino libraries, as well as being the inventor of the Teensy board. And all of his stuff is really high quality, very well written. And the DMX Simple library, which we're using here, this is going to provide the functionality to create the frames of DMX data in the correct format, to handle transmission rates and things like that, so that in our code here, all we're going to do is to simply set the value we want each DMX channel to have and to click send. And DMX Simple will handle all of the behind the scenes heavy lifting of sending that onto the DMX network. Then we go on to the constants. So constants are values that are not going to vary throughout the duration of the code. And most of these relate to telling the code the way in which our circuit has been configured and how our hardware has been attached. So we define two GPIO pins here that are connected to the DMX shield. The first pin here, GPIO pin 4, that's going to be the pin that we write the DMX transmission data to, that will be used by the shield to send it onto the DMX network. And GPIO pin 2, that's the pin that's going to be used to switch the shield between master and slave mode. So we're using the Arduino in master mode, where it acts as a controller that tells other DMX devices what to do. But we could also have configured the Arduino as a DMX slave that receives channel data from another controller. And the way you toggle between those modes is by writing a high or low value to the GPIO pin 2 here. Then we've got three outputs that we're controlling. These are the three linear actuators that are controlled by the GPIO pins between 6 and 11. And these are connected in pairs. So GPIO pins 6 and 7 form the pair that control the first linear actuator. Then we've got pins 8 and 9 and pins 10 and 11. And we're going to make each of those three linear actuators contract or extend by writing either a high or a low value to each of the pairs of these three pins. And we've also got three inputs. So these are the analog inputs that we get from our linear potentiometer sliders, and those are connected to the Arduino analog pins A3, A4 and A5. Now we've got one global variable which I've called DMX output, and that contains an array of three single byte unsigned integer values. So they're going to be between 0 and 255. And these are going to represent the red, green and blue components that we're going to output from our code through to the DMX shield, and that's then going to be passed on to set the colour of the light. So now we get onto our setup functions. This is the function that runs when the code first starts executing and where we configure everything that's going to be used. So we begin by initializing a serial connection, and this is going to be useful for debugging but also for doing some calibration when we first configure the project. We're using analog inputs, and the Arduino has a 10-bit analog to digital converter, which means that in theory the values that we read from the sliders attached to these analog inputs here can vary from 0 to 1023. But you might find that the range of values you actually get reported from these sliders don't quite cover that whole range of values. In my case, I was getting values from about 0 to 900. And one of the reasons for including a serial connection here is that using the Arduino serial monitor, you can examine what values you're actually getting back and then rescale them accordingly into the correct range for the red, green and blue components of the DMX output. We'll see that again in a moment later on. We'll configure the mode select pin as an output and write a high value to it, so that's going to set the Arduino into DMX master mode. And we will also tell the DMX simple library which of the GPIO pins we're going to use to send our transmitted data on that's connected to the shield. Now a DMX universe consists of 512 channels, each of which is controlled by the value of a single byte of data. But you don't always need all 512 channels, so it's a bit unnecessary to send 512 bytes of data if most of them are just going to be 0. So what I'm doing in this line here is explicitly telling DMX simple that in fact we're only going to be using 3 channels of data in our DMX universe, the red, green and blue components of our light. And there's no point transmitting any channels of data beyond those 3. Now I should mention that some DMX light fixtures like to receive a whole frame of data, so all 512 bytes of the universe data, even though they might mostly be zeros. So if you have any problems with your light not behaving correctly, you can just ignore or comment out this line instead by putting 2 strokes at the beginning like that. That will fix any problems, but if you have no problems, I'd leave it here because it just saves a lot of bandwidth of transmitting unnecessary data. We'll initialize the relays that are wired to the actuators, and first of all we'll set them all to output and set a high value to them, but then in the following section what we'll do is we will lower all of the actuators, so their initial state will be in the lowest position. We'll give them 10 seconds to reach that position and then we will tell them to stop. And this lower and stop function, which I'm calling here, they are defined in the section below. So we've got 3 functions to control the behavior of the actuators, all of which take a single parameter, which is the index number of the actuator that you want to control. And they correspond to the 3 pairs of GPIO pins that we defined here. So we've got linear actuator 0, 1 and 2. So to make one of the actuators extend, what we do is we write a low value to the first of its pair of pins and a high value to the second one in its pair. To make it contract again, we do the opposite. We write a high value to the first pin in its pair and a low value to the second one. And to make it stop, we simply have to set the same value to both. Now that can actually be a high or a low value. It doesn't matter, because so long as they're the same, there's no voltage across the terminals of the actuator, so no current is going to flow and it's not going to extend or contract. It's just going to stay exactly where it is. So I've just written a low value, but you'd get the same result if you wrote a high value to both pins as well. Now we get onto the loop function, which is the main body of the code, and this just gets called over and over for as long as the Arduino is powered. And the first thing we do is we want to gather the state of all the inputs. So we read the value of those 3 sliders and we take an analog reading from the GPIO pin corresponding to the input that we're currently reading. So this goes back up to the top to this array of 3 GPIO pins that we plugged our sliders into. If you're using different pins, obviously we need to change that accordingly. And we'll take an analog reading and we'll assign that to something which we called input value. So that's going to be a value between 0 and 1023. Now, when you first set up this puzzle, what you might want to do is now wiggle your sliders up and down and see what values you actually get reported for the minimum and maximum range you're able to record. So in an ideal world, this would take a value somewhere between 0 and 1023, but what you might find is that you don't get that full extent. So the serial.print command will print the value you're getting from all three slider inputs. And what you want to do is to rescale the minimum and maximum that you actually get into the DMX ideal range of 0 to 255. So that's what this line of code does here. So we'll take our input value, which is the raw value that we recorded from the slider. This is the minimum value that you could get as reported by the serial.print line here. This is the maximum value recorded, and instead we will rescale those into the range 0 to 255. And then we will take that rescaled value, we'll put that in a new variable called remapped value, and we will assign that to the corresponding element of the DMX output. So DMX output is an array with 3 elements in it corresponding to red, green and blue, and those are based on our 3 inputs. And then we'll also write that to the corresponding DMX channel. So the DMX simple.write function, like I said, this is a very simple library. It has one function here. This is the channel that you want to write, and this is the value that you want to write to that channel. I'm using +1 because DMX channels use a 1-based indexing system. So the first DMX channel is always DMX channel 1, whereas in our function here and in the arrays at the top here, these are all 0 indexed. So this is our 0th linear actuator, this is our 0th input pin. But by the time we're getting to writing to the DMX channels, we want to start at 1. So we simply add a 1 onto the end of our values here. Okay, so now we need to apply our game logic. So far, we've read our input values, we've remapped them, we've sent a DMX message to turn the light to the appropriate color. Now we need to work out whether to make the actuators extend or not. So that is done in this section of code here. Now, when I first wrote this section, the way I did it was I had a target RGB value for each of the 3 flowers, and then I compared the difference between the DMX output value that was calculated here and the ideal target RGB value of the flower to see if they were a close enough match. But there's actually a few problems with that approach. There's a lot of subjectivity. So there's a lot of color theory involved in that. Human eyes are more sensitive to certain components of light than to others. And some people have differences distinguishing between certain pairs of colors. So I decided to change the approach I used into something a bit more straightforward and explicit. So that's the test that you now see here. And these have got nothing to do with being able to compare the similarity of colors at all. It's literally to do with the absolute values of the 3 components. So we've got our 3 coloured flowers. We've got purple, yellow and pink. And for each one, to determine whether the conditions for this flower to grow have been met, we're just going to look at the values of the 3 elements of our DMX output. So DMX output 0, that is the red component. DMX 1 is the green component, and DMX 2 is the blue component. And again, I got the numbers which you see here, I got these from looking at the output of the serial print statements up here. So I literally moved the sliders up and down until I sort of looked at it, okay, which is the range of acceptable values that I want the light to be in, and determined that the purple flower would grow in that lighting condition. And what I decided was it needed to have some red component, so the red component is greater than 4, but not too much because we don't want it to be bright red, so it has to be less than 12. There's no green at all in the purple flower, so the green component is 0, and the blue component, like the red component, there need to be some there, so it's greater than 4 and it's less than 12. And if all of those conditions are met, that's what the double ampersand means here. This is an and. So if this is true, and this is true, and this is true, and this is true, and you can add as many conditions as you want, we're going to raise the purple flower. We're going to do that by calling the raise function earlier, and we're going to pass it the index number of the first linear actuator. And then we do that with the yellow flower instead. So if that condition wasn't true, we'll go into an else if. So to raise the yellow flower, we want the red component to be, well, I said about more than halfway. Remember, DMX output can take a value between 0 and 255, so testing if it's greater than 128 is saying that it's above halfway. And the green component is also above halfway, and the blue component, well, there can be a little bit of blue in the yellow here, but not very much at all, so it's less than 8. And if that set of conditions is true, then we'll raise the yellow flower. And the pink flower, you see, that's quite a lot of red, quite a lot of blue, and very little green. And in that case, we'll raise the pink flower. Now, if none of these conditions are true at all, then we fall through into the else condition at the bottom, and that simply goes through all of the outputs, all of the linear actuators, and makes them all stop. So you can really make these conditions as complex as you want. Now instead, if you're not using an analog input, if you're using a rotary switch or buttons or something like that, these could be very precise values because you'd actually be dealing with an exact discrete quantity of each RGB component. But if you're using any sort of analog input, like I am here with the sliders or a continuous dial, you'll need to have a degree of leeway within which an acceptable value can lie. But you can really customize these conditions however you want. And that is the end of the code. So that's my flower growing puzzle that demonstrates how to use a set of linear actuators and also how to use DMX to control stage lighting effects. There's just a few final points about this project that I want to address. The first is the question of accessibility. Whenever you have any puzzle that involves colour, the question of how you accommodate players with colour blindness comes up. But that's not really an issue here. The colour of the spotlight is being used as a visual indication of the value to which the sliders have been set, but it's not actually directly used as any input that controls the puzzle. There's no sensor that's reading this value. Whether the actuators move up or down or not is based purely on the position of the sliders. So if you had a scale marked on the input box here, players could set the inputs to the correct positions based on that. And in fact, you could provide that as an alternative or as an additional way to solve the puzzles for players without even needing to look at the light at all. And these inputs don't have to be analog sliders either. They could be digital inputs like switches, multi-way selectors, rotary dials. And if you use a digital input like that, there's no question about subjectivity of whether something is, sort of yellowy green or orangey gold or something. It would be an exact discrete value. Now, I did mention that linear actuators are quite noisy. Now you can muffle this somewhat by putting padding around them in the box, some kind of acoustic insulation, but you can also mask the sound by playing audio from a serial audio player monitor as they move. Or you could use one of the two spare channels on the relay module to trigger an effect. It's easy to know when the actuators are going to be moving because you'll have toggled the state of the appropriate relay channels to make them do so. So it'd be very easy to also toggle one of the last remaining relay channels at the same time to make a sound effect play. And the last thing is about the behaviour of this puzzle. So I set this up so that the flowers only ever grow upwards when placed under the correct light. And in all other cases, they just stay at the same height. The only time the actuators go down again is when the puzzle first starts, or if I press the reset button here, and that will make them return to their fully contracted position. Now, that felt like the right behaviour to me for a puzzle that was about flowers, which typically don't ever get smaller than they are. They either stay the same or grow. But you could adapt this to another theme where something was attracted to the light if it was correct coloured, but if the light was the wrong colour, it actually caused the thing to shy away from it again, contracting the actuator back to the base. And if you wanted to have that behaviour instead, you could do that with a very simple change to the code. So that's it. I hope you enjoyed this video and that it gave you some ideas or inspiration for some tech that you can use in your escape room. As always, I will upload the code listing on the Arduino, the wiring diagram, the list of components and other resources I used all over to my Patreon account, and I'll put a link to that in the description below. If you'd like to support me to create more escape room projects like this, please do check that out. But if you don't want to, if you are unable to, that's fine. I will continue uploading these tutorials here on YouTube, and you're always welcome to just copy them out from the video instead. If you have any questions or comments or suggestions, I always love to hear from you, and I'll do my best to get back to you. Otherwise, I just want to say until next time, thank you very much for watching, and I look forward to seeing you again in the future. Okay, cheers, bye.